Okay, so lesson 55. This will be the last lesson that will be on our test that I'm going to hand out to you guys next week. So complex fractions and the division rule for complex fractions. So turns out we're going to do, what did you call it, Alexa? Invert and multiply, right? So we're gonna start off with this chapter. This chapter is really talking about that. It should be review for us. But let's do a couple of these problems. So we've got AB, fraction AB, and we're dividing that fraction by C. Okay? And we don't want a fraction over a fraction. We want an answer that's at most just a single fraction. So how would I handle this? How would I simplify this guy? The way that I would think about it is I would think about this as a fraction divided by a fraction. How could I think of C as a fraction?
C over 1.
Yeah, any number could be a fraction. We just do that number over 1, right? So if I think of it as C over 1, now I'm going to...
Will you then flip it and multiply it by A?
Yep, exactly. So I'm gonna do, as Alexa calls it, invert and multiply, or multiply by the reciprocal, however you want to think about that. So we're gonna do A over B times 1 over C. We flip this guy, which we call the reciprocal, or you can think of it as inverting it. You flip it upside down and you multiply by it, and then when we do that, we get A over BC. Right? So that's what our answer would be for that problem. Now this other one here actually gives it to us already as a fraction. So we have 1 over C divided by 1 over B. And again, it's still though a fraction over a fraction. Anytime you think of a fraction over a fraction, you should think invert and multiply, or take the reciprocal and multiply. The reciprocal of the denominator. So 1 over C times the reciprocal of 1 over B is B over 1, right? And so when we multiply those together, we just get B over C. So that would be the answer for that. All right, everybody tracking with me so far? Start off easy, baby steps with all of that, right? Let's do one that looks a little bit scarier, but still the same exact rule applies, not any harder. A over X divided by B over A plus X. All right, that one definitely looks scarier. But is the process any harder? It's really not. We're doing the exact same thing, right? So somebody not on the board walk me through what I'm going to write now to solve this problem.
Write A over X, and then write A plus X over B.
A plus X over B, right? And that's multiplied together. The little dot in the middle to signify multiplication. So we're taking the numerator and we're multiplying it times the reciprocal of the denominator, right? Now, this one is a little bit harder as far as the multiplication goes, but not by much. Yep.
Will the two X's cancel out?
They would not. Why would they not? What prevents us from being able to do that?
Oh, because it's added to A.
Because of this addition sign here, right? If there was no addition sign, yes, we can cancel out the two X's. But everything's got to be multiplied together if we're going to be able to cancel out. Okay? Did I hear something else?
Can you automatically just add the A and X?
How would I represent A and X multiplied? I mean, added together.
Just AX.
So like this. Does that mean addition? No, when they're side by side, what does that mean? It means multiplication. So you just changed addition to multiplication. You see why you can't do that? Yep. All right. And we know that when we work it. Remember, these just represent numbers. So if you get confused with some of these rules sometime, just think about plugging numbers in. If A is 2 and X is 3, can I say that 2 plus 3 is the same as 2 times 3? No, right? Those are two different things. So we can't put them side by side like that. That'll help you remember that rule. All right. So what we're going to have to do is we're going to have to multiply A times A plus X. And on the bottom, we can just go ahead and put these side by side because it's just X times B, which we're going to rewrite in alphabetical order as BX. Okay? How do I simplify this top part here? This was, I think you had a problem It kind of tested you on this a little bit. Yeah, it was a little bit more complicated, but this is a simpler form of problem 3 on the test. How do we do that? What do we call this of multiplying the a through to both of these terms?
Distributed.
That's distribution, right? So we're going to multiply the a times each term. A times a is a squared, and then a times x is going to be plus ax, or positive ax, right? Because it's a times a positive x. And so this would actually be our final answer. All right. Any questions about that? So they have a note at the top of page 226 that says many algebraic manipulations can be justified by one of the following. And the denominator numerator same quantity rule. The multiplicative and then the additive property. And this is just kind of refreshing our memory about what things we can do when we're doing algebra. And I just want to, you don't have to remember these complicated names, but I want you to remember what these things represent and what we're allowed to do in algebra. There's really just kind of 2 tricks in algebra. I kind of sum these up into 2 rules right here. This first rule just means I can multiply anything. I can multiply anything by a number as long as I'm multiplying by that number over itself, right? Because what is any number over itself? It's 1. It's just 1, right? And so if I multiply anything times 1, if I do a times 1, what do I get? I get a, right? Anything times itself is still the same thing. In other words, you don't change the value of something if you're multiplying it times itself. And so this rule right here is just saying that one of the tricks that we can often do in algebra is we can multiply top and bottom. I mean, we can multiply something by a number as long as we multiply the top and the bottom of the fraction by the same thing. So we were doing some things like where we had x over b plus whatever, let's see, we'll do b over p, all right? And I wanted to combine those together. And what we did in this case here is we multiplied top and bottom of this one by p over p. This is the way getting common denominators work, right? And then we multiplied this one top and bottom by b over b. And I'm allowed to do that because I'm really just multiplying each term times 1. You guys see that? So what that allows me to do then is say, okay, I've got a common denominator of PB, and so the top part's going to be PX plus B squared. So the reason I'm able to do that is because I'm multiplying these terms by something over itself, which is effectively multiplying it by 1. So that's what rule number 1 says we're allowed to do. These 2 rules right here just basically point out that I can multiply or divide, since division is just sort of the opposite of multiplication. I can multiply or divide, or I can add and subtract anything I want to in an algebraic equation as long as I do the same thing to the other side of the equation, right? So if I have, we do this trick all the time. If I have 3a equals 6, I can divide this side by 3 to get rid of this 3 as long as I divide the other side by 3, right? So that's what this rule is saying. So that gives me that a equals 2, And this rule says the additive property, I can have A minus 2 equals 4. And I can solve that one by adding the same thing to each side. So I can add a positive 2 to both sides to get that A equals 6. Right? Those two basic rules. Whatever you do to one side, you do to the other when it comes to multiplication or division. And you can multiply anything times a value over itself. A lot of algebra problems can be solved just by knowing those two rules and how to apply those two rules. Okay? Any questions about that? And what the little examples I gave you over here? Does that make sense? So those rules you gotta get down, and you gotta get better at using those and recognizing when you use those. Okay? So that's a lot of what we're doing here is just giving you problem after problem to try to do that in different ways so that you get really good at using those two rules. All right, let's talk about finite and infinite sets. What do I mean by finite? If I say something is finite, what does that mean? One thing that you can thank the Lord for is that this class is finite. It ends, right? It doesn't keep going on. So finite means that something ends. If it's infinite, right, we can also thank the Lord that in Jesus Christ, life is infinite. In other words, we have eternal life, right? It never ends. And so infinite means it goes on, never ends. Finite means it does have an end. And so we use that term in math when we're talking about sets. So I may have a set of numbers like this. 6, 7, 8, 9, 10. We call it a set. We denote that by these curly braces right here. I'm not drawing those curly braces very well. It's like that guy there, right? That's what it's supposed to look like. It gets kind of sloppy when I write it quickly, right? But when we put these curly braces on the outside, we say we have defined a set. And this is a finite set because it only includes these numbers, 6, 7, 8, 9, and 10. No other numbers, right? We can count, we can list, we can identify all the numbers that are in that set. But now if I wrote this set here, which represents the counting numbers, 1, 2, 3, 4, 5, and I put that ellipse at the end, dot, 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 that means it just goes on forever, right? So this would be a finite set, whereas this one would be an infinite set. Does that make sense to everybody? Right? Never reaches an end. So with that in mind, let's start talking about sets. And let's say we have these numbers here. And they asked us to represent these numbers as a set B. All right, so we would say B, set B equals, we're doing a set, so we're going to put our little curly braces around it. And when you're identifying a set of numbers, you just put all of the numbers that are in that set of numbers one time, right? So if we've got 0 in there, then we'll only list it once. Same with 1, same with 2, same with 3. So that would be our set that represents these numbers right here, right? All of those numbers are contained within that set. Is this a finite or an infinite set? Finite set, right? So does that concept make sense to everybody? Now if I gave you this, and then I gave you another set D, and I said that set D was set D was that finite set. We could say that set, find the right way to say this here, how they say it in the book. Actually, they're not even doing that yet, so they're not using it with sets, but I'll just go ahead and introduce you guys to this idea. Do you see that we could say that set B is contained within set D? Because all of the numbers that are in set B are also in set D, right? You couldn't say the reverse. Set D is not, one way that we might say it, set D is not a subset of set B, right? Because some of the numbers in D aren't in B, but we can say it the other way. B is a subset of set D because all of these numbers are contained within D, all right? Now the way that the question that they might ask us though, right now, is we may have a set of numbers like this, 7, 15, 0, 1, 8, negative 13, 42. Notice with a set, even though I've been writing the sets in order, it doesn't have to be listed in order. We could rearrange the numbers just to make it easier for us to keep up with what numbers are in there, but they don't have to be in numerical order. And we've got two symbols that we use. We use this symbol to say that something is a member of a given set. So it's contained in that set, and we use this right here to say it's not contained in the set. All right? That's pretty typical in math, right? You'll see some symbol with a slash through it to mean not that thing. Where else do we use this for not? In math, where else do we have a symbol with a slash through it and says it means not? Yeah, we'll say not equals, right? Something can be equal to one another, or we might do it and say it's not equal to one another, right? So that's kind of standard practice to put a slash through there. And so let's say we're given this set right here. We could say for this set, we could say that 15 is a member of set L. That would be a true statement, right? Because 15 is in here. But 14 is not. So for 14, we would have to say 14 is not a member of set L. Okay? Any questions about that? This is just more about just making sure you understand what the symbols mean. So I might give you a problem and say, true or false? 2 is in set L. What would you say? True or false? 2 is a member of set L. Is that true? It's not, right? So we would write false for that. 42 is a member of set L. True or false? True, right? So you may have a problem like that where you just have to identify it as true or false. All right, any questions about that? You guys asked some good questions after the quiz and from the homework because you really sort of set the stage for the stuff that we needed to cover today. So one of the questions that I had was about graphing on the that was on the quiz today, and all of the equations that I've given you so far, where you have to graph something, I've given it to you in a form that looks like this. It's always been solved for y. So you had y over here by itself, and so you have some number in front of the x, and you have that, and then you've got some may or may not have some number afterwards, right? And this form right here, we're going to learn about it in the future. It's called, does anybody know what that's called? Maybe you've learned it in a previous math class. And it's in that form. The variables we actually use for this form are y equals mx plus b. Does anybody remember that? What's it called? Do you know? Does anybody want to know what m represents in that equation? Cohen, you were shaking your head. Do you remember what m is? Okay, m is what we call the slope, and b is the y-intercept. And so we call this form the slope-intercept form. All right, so we're gonna get good at rearranging our equations for lines and putting it in this form so that we can more easily graph it. All right. So in this lesson here, they may give us a problem like this. They may say 3x plus 2y equals 4, and they want us to graph that. And so what we're going to do first, before we do anything, is we're going to solve for y. Not only would that make it easier for us to plug in numbers to it, like I said, it'll put us in slope-intercept form, which we're going to use in the future. And if you happen to have a graphing calculator, this is the way your graphing calculator wants you to enter. Does anybody in here have a graphing calculator? You're like, oh, I don't know. If you don't know, you probably don't. It would be the $100 calculator versus the $20 one that most of us And so graphing calculators, what you'll enter in the graphing calculator is just this portion right here that comes after the y. So we're going to solve this equation for y. This is just like we've done before. We've solved for variables before. So what would be my steps for solving this equation for y? What's the first thing I have to do? I got to get y by itself, which means I got to get y on one side and everything else on the other side. Who said that? Is that correct? Okay. So we got to get y on one side all by itself. All right, that's the goal. So what's the problem here? We got this 3x right now that's connected to it. All right. We want to get rid of our plus and minus signs over here where the y is first, and then we can get rid of any numbers that are in front of the y. So start with the addition, subtraction stuff, and then you'll end with the multiplication, division stuff. So first, we're going to move our 3x over. Now, I've gotten in the habit of just doing that in one step, but I just want to remind you guys, based on the algebra steps that we said just a moment ago, what we're doing, the reason we can do this is because we're subtracting the same thing from both sides, and that's allowed in algebra, right? So if I subtract the 3x from both sides, these go away, and I'm left with 2y equals 4 minus 3x, okay? Now this is not quite the form that we have right here. So I'm just going to change the order of those because we can do that with addition and subtraction. I'm going to write the negative 3x in the front and the 4 in the back. All right? Yep.
You wouldn't write the negative 3x directly over the 4?
You could, but you can't really combine those together, and so that's why I didn't write it directly under it, right? They won't add together. If I'd had an x term here, I definitely would have done it under that x term if I'm writing it like this. But it's not wrong, right? Either place. All right, so do you guys see why I rearranged this? I'm just trying to get it in this form, right? It looks like this. What's the last thing that I have to do to solve for y? What's the problem? Why is y not by itself? Because of 2. So what do I do to get rid of that 2?
Move it to the other side.
How do I move it to the other side? Add, subtract, multiply, divide,
Subtract.
square root. What am I doing?
Subtract from itself.
Is it added to the y? So I don't want to use subtraction. I want to divide, right? Right. These are multiplied together. So anytime they're multiplied together, we have to divide by it. So I have to divide by 2. And whatever I do to this side, I have to do the same thing to this side, right? I have to divide that whole side by 2. Now remember, when you're dividing the whole thing by 2, if I have a plus b over 2, that's the same as a over 2 plus b over 2. So I can write it like that. Instead of dividing the whole thing by 2, I can say I'm going to divide each individual term by 2. So this by 2 and that by 2. Okay? So now these 2's go away, and I'm left with y equals negative 3 halves. I'm going to put that in front of my x here. I'm going to write it like that, just so that it more closely resembles this form here. And 4 divided by 2 is 2. So that would be my simplified version of this equation, manipulating it so that we've solved for y. All right? The goal to this problem was to graph our original equation, which was this guy. All right? That's what we wanted to do to start with. They said graph this. So our first step is to manipulate it, solve for y, make it look like this. And now we're doing the exact same thing we did on the test to graph it. All right? How do I graph this? I want to pick, like I said, I would recommend 3 points. I would recommend almost always one of those points is going to be 0, because that will get rid of our x term. If I plug in 0 for that, what is my y equal to? Just 2, right? If I plug in 0 for x, that term goes away and I'm left with y equals 2. What would be some other good options for x? So that my math would be simplified. Huh? If I made x negative 3 over 2, is that what you said? No, maybe not. I would stick with whole numbers if I could, but whole numbers that are going to make this fraction go away. So what whole numbers are going to make this fraction go away? The smallest whole number that will make it go away is 2. Right? Because if I say y equals negative 3 halves times 2, our 2's cancel out. And so we're left with y equals -3 plus 2, which is y equals -1. So if I plug in a +2, I get a -1 for y. And then I can also plug in a -2. If I do the -2, y equals -3 times a -2 plus 2. Again, these 2's cancel out, but it's a negative times a negative, so we get a +3 here. +3 plus 2 is going to equal 5. So -2 is 5. Do you guys see why I chose 2? It was like our problem that we did a moment ago where we had a bunch of fractions and we wanted to get rid of the fractions, and so we multiplied through by the biggest number that each of the denominators would go into. Well, we only have one denominator here, and the number that this goes into evenly is 2. So that's why I picked 2 there, just to get rid of that 2. So now we have our points, and we're going to graph it just like we normally would. We need to go up to a +5. Right there. We're going to need a -1 on our y, and we're going to need a -2 on our x, and a +2 on our positive x side. So -2, -1, this is x, this is y. I plot these points, 0, 2. Don't go anywhere on the x-axis, I go 0 and then up 2 for the y. -2, I'm sorry, +2, -1, so +2 on the x and down -1 right there. And then finally -2, and I go up 5, so I'm up here somewhere. Right, so when I draw that, I do indeed have a line that goes through all of those points. So this is the same thing we've done before, it's just that the first thing that we do is we rearrange our equation and solve for y. That's really all we've added to this. Does that make sense? All right? All right, this last one's really quick. So I just want to make sure that we know how to do this, and this won't take but a minute, and we'll be done for the day. This problem, we're adding expressions together that have negative exponents. So what if I have ax to the -1 plus y to the -1? And I asked you to add those together and make sure that all the exponents are positive. How am I going to do that? How would I try to add those together? In a problem like this, the first thing you want to do is get rid of the negative exponents. All right? So what does this become if I get rid of the negative exponent there? How do I rewrite a times x to the -1?
You put into a fraction and flip it.
Yep, so this is going to be a, and the x goes to the bottom, right? That's how I get rid of that -1. And I'm going to do the same thing here. I'm going to have 1 over y to the positive 1 instead of right? So I just move it to the other side of the fraction. Now, once I've done this, now I've got the same problem that was one of your problems on the test, right? Where you're trying to combine two fractions together with different denominators that have variables in it. And so to combine these together, I'm going to get a common denominator, and the common denominator here would be xy, so I'm going to multiply top and bottom by y for this one, and I'm going to multiply top and bottom by x over x for this one, all right? So that on the bottom of my fraction, this right here, is going to be equal to something over xy. All right, that's what these two multiplied together would be. So that's going to give me a common denominator of xy. So my first term is going to be ay. My second one is going to be 1 times x, so plus x. So that would be my final answer for that. All right? So these all work the same way. Your first step for these is always going to be flip your negative, whatever variable has the negative exponent, flip it to the other side of the fraction, and then do the step where you get a common denominator and add them together, which was what we had, and that was like lesson, I don't know, one of the lessons, maybe the lesson from last week or a couple of, it was something you were testing on the day, so it's been within 49 through 53, right? So as long, after you do the flip here, the problem's the same problem you've done before. Does that make sense? Think you guys can do that? We'll have some practice.